If you look at mechanical clocks and watches, as opposed to your quartz watch, there's no electricity, there's no electronics. So they all are based on what you call an oscillator. So your watch has a balance wheel and a spiral spring with an oscillator which goes back and forth. And that's the time base. That's what gives accurate time. This is your balance wheel. If you don't give it impulse, then it eventually stops. So there's two things you have to do. This precisely has a constant frequency, which is what gives good timekeeping. And you have to do two things. You have to keep it running and you have to measure the number of oscillations. So in order to do that, you have an escapement. So you've got an energy source, which is another spring, the main spring, and that energy is passed through the transmission, and then in between you've got the escapement, in this case the Swiss lever escapement, which does two things. It gives energy to the balance wheel to keep it going, and it also counts the number of oscillations. So this is the energy source. So here you see the balance wheel going back and forth, and then this anchor stops the movement and makes it start again at a constant rate given by this time base. So you can also hear the ticking. This is how every single mechanical watch works. In your mechanical watch, the movement is actually completely stopped for 90% of the time. So the balance wheel keeps on turning, but the movement is stopped, and then it's liberated and it speeds up, and then it stops, and the ticking is the crashing of the movement when it stops. That's a waste of energy. And also the stop and go motion intermittent means that's why mechanical watches, the second hand doesn't move smoothly. You can see it sort of fluttering. It's moving 8 times a second in a normal watch. And the escapement, because of the crashing and the stop and start, is inefficient. It's the efficiency is about 35%, which is not very good for a mechanical transmission. And then there's the stop and go motion. And then the escapement is what you call a feedback system. So it's actually quite complicated to build, and only the greatest geniuses in watchmaking have been able to do escapements, and they're all compromises. The mechanical watch is essentially conceptually unchanged in the last 200 years. The watch of 1820 is pretty similar to the watch today's, except that the watch today is 10 times more accurate, much more reliable. That's because every single detail has been improved. Watches today are almost accurate to 1 second a day. That's very precise. So in order to build a good watch, you gotta take care of every single detail. The friction, the gears have to be done almost perfectly, and has to be resistant to shocks and temperature. All these things have been figured out in the last 200 years so that the watch today is extremely good. Our job is not to replace watchmakers, it's just to propose new concepts. So instead of competing directly with watchmakers who are extremely good at what they do, what we're doing is to do differently than the watchmakers. We can't compete against them at their own game. So we improve the escapement by completely eliminating the escapement, which requires a new way of thinking. So if you look at the classical time bases, there's, for example, the balance wheel. You see that it's going back and forth. The other time base for a clock is the pendulum, which also goes back and forth. In your electronic watch, you've got every electronic watch, quartz watch, has a little quartz tuning fork. And also, there's 2 blades, and they also go back and forth. And the reason is that the movement is 1 degree of freedom. Here it can only move at an angle. That's 1 degree of freedom. If you're trying to move in a restricted place, to oscillate in 1 degree of freedom, you've got to go one way, stop, and then go back the other way. That, in order to give impulses, And to keep it going, you've got to give it intermittent impulses. So you got to have an intermittent escapement. This is the way it is. However, our new concept was to have an oscillator like this, in which you have 2 degrees of freedom. So you can go in the one direction and you can go in the other direction. Once you do that, then you can have, the oscillator can move in a unidirectional trajectory, like a circle or an ellipse. Once it moves in a unidirectional motion, then you just use a crank, and there's this pin here goes inside the crank, and then you just turn the crank, and it's the crank that keeps it going. So that whole complicated Swiss lever escapement has been replaced by just this, the crank. So you've simplified the escapement. Now you can't simplify everything. Here, the oscillator is just a spiral spring and a balance wheel. So the complication went into the oscillator. So our oscillators are what is complicated. However, what you gain is that there's no more ticking, and the second hand, instead of stopping and going, it flows naturally. So here's our clock. So this is one of the 2 clocks that we built using this concept, and you notice we did a big second hand in order to point out that the second hand is flowing continuously. It's not stopping. So that's the IsoSpring concept. This clock is completely standard. We took just an old clock and we just removed the movement, and then we put it in here, and there's a driving weight like in a grandfather clock, and then this had a pendulum that you could see swinging over here. So we removed the pendulum and we put our oscillator, which in this case is a sphere, and we put it on top because we want to show the oscillator. It's the showpiece of the clock. Before, you could see the showpiece was the pendulum, which was below.